Okay, this is example, this is exercise number 30 in our book. Again, it's computing the derivative of a function. So we want to find the derivative of the function h of t. So we'll call that h prime of t. And again, technically this is a different formula, but just trivially different. I mean, the function's called h instead of f, the variable's called t instead of x. So it's really the same formula we have, except now we probably say the limit as delta t goes to 0 of h of t plus delta t minus h of t all over delta t. Okay. So the x is changed to t's, the f changes to an h because that's the name of this function, but it's really the same formula we've had. So again, let's see what do we have here. Well, limit as delta t goes to 0. Of course, we can't put 0 in for delta t because we get division by 0. Okay. Well, we can put t plus delta t into this function. We get 6 minus 1/2 t plus delta t. Okay. Minus the original function itself, 6 minus 1/2 t all over delta t. Okay. So limit as delta t goes to 0. And let's see what we got here. We got 6 minus 1/2 t, okay, would be minus 1/2 delta t, just distributed the minus 1/2 into both terms. Okay, minus 6 plus 1/2 t. Okay, again, just distributing the minus sign into the second term as well. And again, a lot of stuff cancels. The 6 and the negative 6 cancel. The negative 1/2 t and the positive 1/2 t cancel. And in fact, if you look at all I have left, it's just negative 1/2 times delta t over delta t. So those cancel, and what I wind up with here is the limit as delta t goes to 0 of negative 1/2. Well, if all of the delta t's are gone, then this number is going to approach negative 1/2. Okay, so what does that mean? Well, that means that the derivative of this function, thing we would call h prime of t, is negative 1/2. Now, since the derivative is a constant, it means that the slope of this function is always negative 1/2. If you look carefully at this function, you might recognize that it's a linear function. It's the equation of a line. Okay. Well, that's in fact what makes lines special. They have a constant slope. So this function is a line with a slope of negative 1/2, so the derivative is a constant, negative 1/2. Okay. Now, if a function isn't constant, the slope probably isn't either, and the derivative would involve the variable as well. Okay. But lines, of course, have a constant slope. We know that already. Okay.